Hey guys, so this will be a continuation of chapter 7 to finish up the chapter. And we left off with this scenario, this general equation for force. For work based on the force and the distance traveled. And in the most general sense, the work the work is given by the force and its displacement at each individual point. And as an approximation of the integral, what we do is we calculate how much work approximately is done in each one of these sections, where each one of these is delta L, right? And then the work for each one of these sections is given by the function cosine, not the function cosine, the force multiplied by the cosine and between cosine of the angle between the actual force applied at that particular point and the distance. So here we just take the average force for that particular region, and then we take the average angle, and then we just calculate the work at that particular for those particular averages, and then we scale it up to the size of our interval that we're looking at, and then we add up all these other points where we have some force too. Maybe the force changes along the way. In this region, it may be different, so we do F2 times cosine theta 2, that's the new angle, and then we add it up, and it comes out to equal this integral. When we make these intervals small enough, it ends up being equal to the integral, right? The integral is just a sum of the area under the curves. So in the most general sense, it's given by this formula. Now, and what we could do, because of this dot product, right? We could write the force we could break up the force in terms of its components because of this dot product. So if the force is equal to this, let's say it's given fully in terms of its in terms of unit vectors. So we have the force in the x direction, and then the y direction, and then the z direction. And then we're given the path that's taken, and usually we write it as dl, but right now this path is not defined. dl right now, this vector, it's a generalized dl. We never define what this path exactly is, right? And we'll just use a function to define this path. And here we'll keep it simple. We'll just write dl is equal to, in the x direction, is the change in the x direction, plus for the y direction, this the change in the y direction, and then this is the z. This will generally be one of the simpler forms that you see for dl. All this is saying is that dl is just made up of the changes in the x direction, the y direction, and the z direction. In general, this function can depend on other variables. Like you can have an x dependence in the y direction as well. So it doesn't have to be exactly like this, but it could be more general than that. But this is one of the more simpler cases where it's just the change of L is just the change of X, Y, and Z. And then if it's like this, and then the work ends up coming out to be, you can break up the integrals, the vectors into the different integrals. Right? When we take the dot product, we get rid of the direction, and then the dot product, you just multiply the terms in the same dimension, along the same components. You multiply the same components together. So then the work would be given by the beginning at the x coordinate to the end of the x coordinate from xb to xa, and then this would just be the force in the x direction dx, right? It's just the dot product between these two is multiplied, and then we add up the same thing for the y. And then as well for the z. X f z times dz. All right. So generally, we'll break for a complicated force that's in multiple dimensions, and let's say if it travels along multiple dimensions, we like to break it up, the work, into the work done in the x dimension, the work done in the y dimension, the work done in the z, and then we can just add up the total work at the end, because this is a scalar quantity, and we just care about the work that does not have a direction associated with it. Get rid of that vector there. Okay? This is a scalar product, so we can just calculate the work in each of the dimensions and then add it up for the total. So that's that. Okay, so now let's look at another system that we'll be looking at extensively now that we have this definition of work, and it's a spring. So basically, the fields that we've been working with is just the gravitational, this gravitational field that provides this force, right? And then we could also apply forces using our hands, but we don't really understand that force that well. We understand the gravitational force now that we went over the universal gravitational law, right? And it's just 1 over r squared. But there's another simple system that stores energy and releases energy and can provide a force, and that's a spring. Right? So a spring is just a coil of metal or some elastic material, and we mold it when it's made into this helical pattern, and then when we heat it up, the atoms rearrange themselves to stay in the shape, and then when we cool it down, they're sort of frozen in that shape, right? So they will always want to go back to this original shape that they were molded into, in this case, this helical pattern. And these springs want to be a certain distance apart, right? Now, if I push the springs together, what will happen is that it will want to go back to the original shape. I'm literally, the elasticity comes from interactions between the neighbor and atoms, right? They want to keep that original shape. When I compress them, I'm introducing a change to their original orientation, and they, through electromagnetic forces, they end up pushing, having a reactionary force basically to this, and they provide a force that's resisting my original compression of it. So they always want to restore the spring back to its original shape. And this is called the restoring force. So why is it restoring force? If I compress it, the spring will want to spring back into its original position. Also, if I stretch it like this, if I make it longer than its original position, it will want to pull it back into the molded orientation that it started with. So whether you compress it or you extend it, it will want to restore itself back to its original form. So this is known as a restoring force. So any displacement away from this equilibrium position, right? Let's call this H for now, right? If this is the equilibrium position, the spring exerts a force anytime it's away from this equilibrium position, right? So if I extend it, right? And then this is X. Let's call this equilibrium position. X is equal to 0, right? So if I extend the spring and I pull back on it, somebody's hand pulling back, right? And I extend it amount X, right? It's going to want to provide a force going in this direction, right? And this force was found, so I extend it, right? The force of my hand. So, okay, so let's draw a force diagram. I'll draw it up here for this, right? I'm pulling it back, right? So my force, FP, is providing a force backwards. Now the spring provides an equal and opposite force forwards, assuming that my hand's not accelerated or moving, right? And this provides an equal and opposite force backwards. And we'll call that Fs for the spring, right? Now, this was found originally empirically, and it works extremely well for small displacements of the spring. And we have this. Well, if we're not moving the string, then we have Fp is equal to Fs. And then Fs, if we actually measure the force that we apply, Fs turns out to be K, this value K times X. And X is the displacement from equilibrium. So it's really a delta X. It's from its equilibrium position without any force applied, right? Now this K is called the spring constant. All it is a proportionality constant that relates to its displacement to the force, and this is measured empirically. The spring constant is very complicated because it has to do with the microscopic structure or the atomic structure of your material, and there's other and then also it has to do with well, I guess it's just basically the microscopic structure. There's a lot of different components to that, like how well is the material, what's the impurities in the material, how well are the atoms ordered, like what temperature did the spring go up to, and then how fast was it cooled. So if you ever seen somebody dip in a sword or a piece of metal into water when it was red hot, it's called quenching. And what it does is that it freezes the atoms in place in that particular position. When it's very hot, the atoms are mobile and they can move around. And once you stick it in, they freeze into that location. There's a special way that this is done so that the material is as strong as possible. But and all this goes into K. But this can be measured empirically by pushing on the force and then measuring it as a function of X, right? You just measure the force at different points for this position x, and you measure this force, the person force. Then you get this slope. You got a linear equation, and then you fit it to k. But and this only works for when you stretch a spring so long. If you ever had a cheap spring from like a pen or something, and you extended it much longer than it was supposed to be, if you notice that it takes a different shape, this equilibrium position will change, and the spring will lose its spring constant. It will change. So when you displace it a lot past a certain point, this no longer holds. Then your k is changing as well. And that becomes a function of x. But for us, we just consider these scenarios. And then likewise, let's say if we compress the spring, and let's say if this is at the same distance, x, right? What's the force in this case? Well, the force on this is, I'm pushing in, so now FP is going this way, is going to the left, and FS is now going to the right, so it reverses. And if you look at it, if this is our 0 point, this makes sense, right? Because if it's dependent on this, right? If it's dependent on this equilibrium position, here I changed x in a positive position. Really, we should write this, delta x. And here, delta x is x minus 0, right? And then we have this delta x, to change it from the equilibrium position, right? And then here, we have 0 and then minus 10. Or I should rewrite that. Minus x minus 0, right? Because we're going in the other direction. We call this positive, so this way is negative. And then we end up getting a negative kT for this, right? And this is how the forces on the spring work. The more you compress it, the higher the force is, right? And it's linear with the distance that you compress it. Okay, so now let's figure out, and this is called Hooke's equation. This is the spring equation. This is Hooke's law. Write that down. Right. That's Hooke's law. And we'll use this equation over and over again for springs. Okay. So let's figure out what the work is on this. Right. So let's start off with the general formula for work. It's from A to B, force dotted with dl, right? And this is the work. So in our case, what's the force? Well, the force is just Hooke's law. I'll just leave x instead of delta x. We'll take the equilibrium position to be 0. dl now, right? Here we'll only be working with one dimension, so we don't really have to worry about this dot product. dl here is just dx, right? So then our work equation becomes this. F is just kx times dx, right? And then let's integrate this. So this, I integrate it. That means I pull, make it 1 power higher, right? So you get kx squared. And then, of course, from A to B. So in general, the work done on a spring or by a spring depending on whether you're releasing the energy from the spring or you're actually compressing it or extending it into a certain position. It's given by this. So the work in general is given, and here, let's say that A and B, let's say A, we start at 0. We start at the equilibrium position, and then we extend it out to X. So B is equal to X, right? So this means that if we start out at 0, we finish at X, Kx minus 0, right? So the work done on the spring by the person is equal to how far you extended it squared. It's equal to this, right? Because initially there's no work involved with it, and then we add energy to the system is what we say, right? Now, if we had a little latch where it would stay in this position, let's say if we had a little latch, we compress it and then we keep it in that position. Right now, it's storing energy, right? As soon as we release this latch, it's gonna apply a force to whatever's on the end of the spring. So right now, we say that it's storing energy. We put energy into the spring, and it wants to be released. You know, just provided a little impulse, moving this latch out of the way, and it'll provide some force and acceleration to whatever's on the end of it. So we say that this stores energy. And we say the same thing actually for the gravitational field. The fact that I'm taking something up a hill, and bringing it to a higher height, right? It has the potential to fall down, back down to, the height that I started at the bottom of the hill, right? A ball has the potential to roll down and pick up energy from the gravitational force, right? So when you bring objects up to a higher height, you're really storing energy. You store this energy, this work that you put it in, or energy, you're storing it in the gravitational field. And we'll use this concept in chapter 8. But let's finish with work. Okay. Hello? Okay. So I want to make sure the mic is on. Okay. And this brings us into the work energy principle. And here, this is when we really first introduced this thing called energy, which I just started talking about. And energy is one of the most important concepts in physics, and we use it all the time, especially in modern physics, to explain behavior, to use it to actually mathematically explain behavior, right? Two things can only really exchange energy if their energies are about equal. And we use this all the time. In atomic physics to plasma physics, all over. So, now, what energy exactly is it's hard to define. And usually the best way to define it is the ability to do work. is when something has energy, it has the ability to accelerate something, right? Has the ability to do work. Now, it's a certain type of acceleration, right? It has to provide a force over a certain distance, right? And this force has to be along the same direction. Right? And in general, what we say is when something is moving, we say that there's a certain energy associated with this movement, right? Remember how I was saying at the ball at the top of the hill? So if we have a hill, right? I walk this ball all the way up the hill, and I go up to the top. And now the ball sits at the top of the hill. All the work that I did, now if you remember the work that I do to bring the ball up here, we did this problem with the backpack, right? This is just equal to mgh. That's the work that I give to the ball to bring it up here. Now this energy is now stored in this gravitational field. We'll go into it more in a little bit, right? Now, if the ball rolls down this hill, right, it loses this mgh, and it becomes kinetic energy. And what we say is that this movement of the ball has a certain energy associated with it, right? This ball can hit another object, a bigger ball, and move it, right? It provides a force and it starts moving that ball. It can provide work, right? So so the motion of this ball can transfer its energy to this larger ball or whatever's down here and move it, right? And do work on it. So there's a certain kinetic energy associated with its movement. And this is called translational kinetic energy. Now, let's derive this real quick, right? So if we have a net work over here and a net force, right? And generally, if it's along the same direction, let's assume that the force and the work is along the same direction. Then let's rewrite this in terms of ma times d. It's acceleration times its mass, right? Now let's convert a into its velocity. It's moving at a certain velocity down the hill, right? And once it gets down the hill, it's moving at a constant velocity. There's no other, gravity is no longer doing work on it to increase its speed, right? So what that means is that from the kinematic equations, right, the velocity that we finished on is equal to 2a plus d, right? This equation, right? And if we start out at, now let's solve for a just comes out to be squared minus 1 squared over 2d. Right? Now let's plug it into here. M times v squared v1 minus 2d times d. And then let me just erase this. We don't need it any longer. All right. And we have this. The d's cancel out. We're left with 1/2 mv squared we end up with this formula. So the net work done on an object is its change in velocity squared, basically, right? How much does the velocity change, the velocity squared change from this point to this point? That's how much work is done on that ball. So if we start up here at the top, there's zero velocity. So the net work done on this ball, which is mgh, this distance, let's say, we bring the ball from the bottom, right? mgh, the net work done on the ball, is equal to the change in its velocity. And if it initially starts at 0, right, that means all the work goes into its velocity, and then and we could calculate the net work by using its velocity. So the energy associated with this ball, when it reaches the bottom, is this. This is how much energy it has. This is called the kinetic energy. We'll use it over and over again. So the kinetic energy of the ball is just given by its velocity squared, right? And then the change in kinetic, the net work done on the ball is equal to the change in kinetic energy. You can either call it K or KE. The book uses K. I normally use KE, but I'll go back and forth. And so then the net work done on the ball is just the change in its energy, right? And the total kinetic energy is just given by its instantaneous velocity at any given point, right? So the work done on it is the change in its velocity. And this is called the work energy principle. Where the work energy principle, it's on page 173, the work energy principle states that the net work done on an object is equal to the object's change in kinetic energy. So the work done, we just literally derived it. So the net work done on any object can be measured by its change in kinetic energy. This gives us a really good measure for how much work we actually apply to something, right? All we have to do is measure its velocity, and we can figure out how much energy, kinetic energy has. And then if we measure at 2 points, we can measure the work that was done in between those 2 points, 1 and 2, right? Here, 1 and 2. And then we can calculate how much work was done on the ball. Okay, so why don't we do a simple example? So let's do 7-7. This is not this section. This is section. So and here, okay, so so we throw a baseball. The weight mass is equal to 145 grams, and we throw it so that it acquires a speed of 25 meters per second. V is equal to 25 meters per second. Before we throw it, the velocity is 0. And then after we throw it, it's 25. Let's label it V0, V1. Okay, it's 25 meters per second. So first they ask, what is its kinetic energy? What's the kinetic? What's the kinetic energy? And here we just take the formula for it. So it's 1/2 the mass times the velocity squared. And here, so then we plug it in, 45, it's 25 miles an hour. And its energy at that, right after we release it, is this, it's given by this. And this ends up equaling 45 joules. Right? And that's the energy that's associated with the ball. Now, the second part of the question is, what was the initial work? The net work done to get the ball to the speed of 25 meters per second. What was the net work done? And here, what we would have to do is calculate the change in kinetic energy. All right, so how much kinetic energy did the ball have to start with initially, right before we start throwing it? Right? That's our initial kinetic energy. And the net work that was done is this change in kinetic energy. How much energy do I add to the ball? And here, we start off with a velocity of 0. So we obviously know that the velocity initially is 0. So all this energy is is what we add to the ball. So if the energy of the ball is initially 0, and now its final kinetic energy is 45, that's how much work we put in, right? Because initially there's no energy. So, and basically that's the answer. So these energy problems are pretty simple. The concepts are much more simpler than the kinematics and even forces, because the reason why it makes it so simple is because this is scalar quantities. We're just dealing with numbers. We don't have to deal with directions and trigonometry. And that's really the value of working with this energy, is that it's a scalar product. It makes our lives easier. So, but let's explicitly write it. So the net work done is equal to the change in kinetic energy. And this is equal to its initial, the mass initial, 0 squared, or so say 1 minus its final minus its initial, right? And then we know that V0 is 0, so this ends up equaling this, and then it ends up being 45 joules. Okay? Now, if you look at it, it's very interesting. The velocity is squared here. So that means if you have if you're going twice as fast, your energy increases 4 times as much, right? It goes by this power law. So this means that when you get into a car accident at 10 miles an hour, the energy or the work that the car gives to whatever object it hits would be 4 times as less as if it was going 20 miles an hour, right? If you compare a car going 30 miles an hour to a car going 10 miles an hour, right? That's 8 times as less, right? Or I'm sorry, 9 times as 8. Right? easily calculated. So it doesn't obey this proportionality, right? It's a power law. So a car going between 10 and 30 miles an hour, there's 9 times as much energy in that car. So see with that car, right? Now, if you compare it between 10 and 60, you know, it's 6 squared, so it's 36 times as much energy. So that's why it makes a big difference between if somebody's going 90 miles an hour if they get into an accident compared to somebody who's going 65. So that's why it's such a large difference. Okay. Okay, so let's do another simple problem. Okay, how much work is required to accelerate a 1,000 kilogram car from 10 to 20 miles an hour? So we want to increase the velocity of the car. So 7, 8. So all it is that it's the difference in kinetic energy from the initial point, right? The car is, the mass is 1,000 kilograms. Its initial velocity, I'm just going to write initial here, or I'll write 1 and 2. Its initial velocity is 20. Its final velocity is 30. Oh, no, now we just calculate it. So it's 1/2 the mass times V2 minus V1. Right? And then we can pull out the masses and the 2's. We get 500 minus multiplied by 30 squared minus 20 squared. Right? So we get 500 times 900 minus 400, right? And this is just 5 times 5, so it's 25 or 250,000 joules, right? So it takes a lot of energy to speed up a car to go in 30 miles an hour. Compare this to the ball that we throw, all right? That only took 40 something joules, 45 joules. Compared to a car, just increasing it from 20 to 30 miles an hour takes 250,000 joules. So. All right, let's do this next problem. It's quite interesting. So now, let's say if we have a car, right? This car, if I want to have it brake from, let's say if I brake it from 60 kilometers an hour to stopping, to make it stop, right? I do it within a distance of 20 feet. Now I want to say, okay, what will my car be like? How long will it take to brake if I'm going twice as fast? If I'm going 120 kilometers per hour? What is the stopping distance? How long does this distance have to be, right? Now, we assume that the braking force is independent of speed. So the force, our de-acceleration force is constant. Or yes, the de-acceleration force is constant, right? And then, so if I'm going 120 kilometers an hour, what is this distance? What is that distance? Right. So let's figure it out. So we're going to have to relate it. So how do we go about this problem? Well, what we want to do is, all right, we have to figure out how much work is done on this car to slow it down to here, right? Then we can figure out the force. And since the force that's applied to this car, the de-acceleration force. Once we have the de-acceleration force, we can calculate the change in energy in this system, right? And this change in kinetic energy we know is equal to the work. Then if we have the work and we know the force applied, we can easily calculate the distance, right? Just from the definition of work. And that's what we'll do. So let's figure out what the network is first. All right, so the network in this system is equal to the force times the distance, like we just said. And then the cosine 180, right? Because our force is going out, is actually deaccelerating. It's the opposite way. So the network on the system is going to be negative, right? We're taking the work we're taking the energy out of the car. So this is the work done by the brakes on the car. Okay. Then, by the work energy theorem, which I had up initially, we can relate the network to the change in velocity, and that's just the change in velocity, or the change in kinetic energy. And that's just equal to these two, right? To this, what we had up on the board earlier, right? And then our velocity at the end is 0. So V2 is 0 in this case. Right? This is V1, V2. Right? So then in both cases, V2 is 0. So we end up with this. Our initial velocity is just equal to this initial velocity, right? Then, right? So now let's go back to what I said originally. Let's calculate the work done initially on the car and the work done initially on the car is 60 kilometers per hour. I'm writing this in because we don't normally use that quantity, right? And then this is equal to FD. Let's calculate what D is. So So this is around 16 kilometers per second, 16 meters per second, 16.6. So let me do the calculations. This is for a 1,000 kilogram car, and then 16.667 squared. So, and then we'll divide this by, we'll divide this, which is 9 joules, and we'll divide this by the distance. So this is 20, and then we'll get our answer. And so the force applied by the brakes is this, right? Now we'll go up to our other, we'll go to, so this is scenario 1, this is scenario 2, right? So this is scenario 1. Now let's go to here. Let's plug it in. So we have F net is equal to the change in kinetic energy. And in this case, it's M times 120. Now this is just, I'll just take it out. This is equal to twice this speed. So this is really 4 times the square. I'll write it like this because I already have the numbers. So it's 4 times this quantity here, right? So it's just 4 times this. And then it comes out to be 5.6 times 10 to the 5th, right? Joules. So now this is the amount of joules we have, right? And then this will equal to F times D, right? And then we know F, we calculated D, so then D would be divided by F, and let's calculate that. F in this case is now 9. And it comes out to be 80 meters. So if we go double as fast, how much further do we have to travel to slow down? 4 times, right? And this is because of the square. Look, you see that 4? I just quadrupled the kinetic energy. So that means if I'm applying the same braking pressure, it takes 4 times as long to slow down. This is why they say that every 10 miles an hour, you double the distance that you're away from the car in front of you. This is why, because it's just a good rule of thumb to follow this, to follow, given the power law, right? So from going from 60 kilometers an hour to 120, or 30 miles an hour, roughly 30 miles an hour to 60 miles an hour, you need 4 times the same distance to slow down, right? And that's why they say you should double the distance every 10 whenever you increase the speed by 10 miles an hour. Right? So you have to be careful of these powers. Things are no longer intuitive when you deal with these powers. Okay. See what this last problem is. Okay, yeah, let's do this last problem. Okay, we have a compressed spring. Let's say we want to compress it, this spring, right? And it has a block on it by 100 and by 11 centimeters from its equilibrium position. I'll make x equals 0 over here. That's its equilibrium position, and we compress it, right? Part A is, what is the net work done? What is the net work done on the spring to compress it? All right. Well, let's draw. So the spring, they give us the spring constant is 360 meters per newton, newtons per meter, right? And now what are the forces on it? So there's mg, of course, right? At this point, there's an fs, which is just equal to kx, right? There's the normal force, Fn, and then there's also a drag force, a frictional force. We'll call that Fd. Right. So the first question is: once we compress the spring, how much energy does it have in it? And here we just use the formula, right? Which we derived already, right? And it's just equal to 1/2 kx, right? This looks actually very similar to the kinetic energy, but instead you have the k instead of mass and then x. So the work done is equal to kx, right? And here we're compressing it from equilibrium, so we just use this, and it's equal to 1/2 360 times 0.11 centimeters, meters, right? And we got our answer of 2.8 joules. Okay. Now the second part of the question is, so if the block at the end of it is 0.85 kilograms, or I'm sorry, 1.85 kilograms, what is speed of block when at position. Ignoring friction. Right? So, okay, so we look at this. What is the speed when it reaches equilibrium position? Well, let's figure this out. Right? So the spring does 2.18 joules of work, right? When it gets back to its equilibrium position. Right? So if we did this much work to compress it, and then when we release it, if we ignore friction, the only thing that does work on this block is the force due to the spring. So this means that the net work done on the spring by me initially is the only thing that does work back on this block. It doesn't lose any other, there's no other work done on the system. So that means that this same amount of work that I put into the spring is put back into the speed of this block, accelerating towards the equilibrium position. And this, so then we just equate these two, right? So here I solve for the kinetic energy. Ke is equal to 1/2 mv squared. Ke is equal, then, I'm sorry. Is equal to this. So the velocity is 1.4 meters per second when it gets back up to equilibrium. And this is because there's no other forces on the system besides the spring force. So whatever work that I put into the spring, it gives back, right? It stores the energy, like I said earlier. And then it could release it and put it all back into the block. And if there's dissipative losses, like friction or air resistance, we could just take it into account, right? We calculate the total work done, and then we subtract off any dissipative forces, and then we could use this. But we know that its energy, right, will be just the net work done on it, and then we could use this formula to figure that energy out. And that's what we'll do. Okay, so and we'll do this for part C. So it's the same thing as part A without ignoring friction. So C will be the same thing. With friction now. So now, right, the net work done on this system that comes back to here is two things, right? So we have two forces. We have in the horizontal direction in this case, so the x direction. We have the force due to friction, and we have the force due to the spring. So our F net will have two components of the spring, right? I'm just gonna write these two terms: the work done by the spring plus the work done by the friction, right? So we know the work done by the spring is just equal to this, the 2.8 joules, right? We know the work done by the spring. I'll put a subscript S there. So this is how much work the spring does, right? Because that equilibrium has no more work left in it. So we'll just write 2.8 joules multiplied by added to the work done by the force. So the force is this way. It's pointing away from me. And our movement, our displacement is in this direction, right? So based on the work, the relationship between work and force, we would have this. It's the force, Fd, times the distance, which is 0.1, times the angle between the displacement and Fd. Now, Fd is pointing the opposite way as our displacement, which means that this angle is 180, right? This is Fd. Keep writing FG. Fd, and this is this D. So that means that Fd dot D is equal to the magnitude of Fd times D times cosine 180. Right? All right. We'll use that. And then that cosine 180 changes this to a negative sign. And we end up getting this. And then I'll plug in the numbers over here. This will give us a negative 0.77, right? 0. So now the total work, the net work done on the system is 1.41 joules, right? Because the spring does work on this dissipated force due to friction. So the spring does work on friction, and it has less energy. So this is the energy that the net work done on the box by a combination of the spring and friction. And now this will be used for the speed at the end. Now, if this is the net work done on here, the work energy theorem tells me that this change in the net work done on the system is equal to the change in kinetic energy. Right? And we have V1, V2 minus V initial. V initial is 0, right? We start with the spring compressed. We just let it release. So this is equal to its final velocity, M2, and that's what we're looking at. What is its final velocity? And then this is equal to the net work. So then we find, we'll just use the equation that we had on the board earlier, and we'll find, we solve for V2, and we'll get F net over M, and this will translate to 1.23 meters per second. Okay. So that will finish up this chapter, and we'll continue on Tuesday. And then if you want to look at the general derivation of the work energy principle, please do. That's the more rigorous derivation of it. What I did was not as rigorous as what is acceptable for, finding something in science. Because we made some assumptions in it. But that finishes up chapter 7. And we'll move on to 8 next time. Okay. Take care, guys.